Intermediate Algebra, Section 9.3, Solving Certain Logarithmic Equations. Many logarithmic equations can be solved by rewriting them as equivalent exponential equations, and that's exactly what we're going to do in these logarithmic equations. Logs typically look foreign because we haven't worked with them much, but if we can translate them into an equivalent exponential, perhaps we'll have a sense of where to go. So, our base here is 2 raised to the 5th power is equal to x. The only thing to do is simplify here. 2 to the 5th power, 2 times 2 times 2 times 2 times 2. I think I said it 5 times. Results in our unknown x value equaling 32. In this next problem, we're given log base 10 of x is equal to -2. Our variable's in the same place, but we'll use the same procedure. We'll translate this from logarithmic form into exponential form. Our base that we're taking the log of will act as our base on our exponential form. Raised to this power is equal to x. 10 to the -2, to get rid of that negative exponent, we'll drop that to the denominator, so we have 1 over 10 squared. 10 squared being 100, so we can answer x is equal to 1/100th, or if we want to put it in a decimal form, we could write it as 0.01 100th. In this next example, our variable is here, but our strategy will be the same. Translate the logarithmic form into an equivalent exponential equation. So we will have the base of the logarithm act as our base, raised to an unknown power is equal to 16. We'll use the principle of exponential equality, which is essentially saying if we have common bases, we can set exponents equal to one another. Can we do something with 16 to transform it into a base of 4? And as it turns out, we can, since 16 is 4 to the 2nd power. Then, because we have common bases, we can set our exponents equal to one another. So y, our unknown exponent, must be equal to 2, and we've simplified the problem. If y hadn't jumped out at you, given this equation, another possibility might have been, if you went for prime factorization, 2 is 2 to the 2nd power raised to our unknown y. 16, if you do a prime factorization, is 2 to the 4th power, since there are 4 2's multiplied together to give us 16. We still have the same principles of exponential equality, which says if we have bases equal to one another, then the exponential powers must equal one another. So here we would have 2 times y. If you recall the exponential rule, power raised to a power, you multiply exponents. So we have 2 times y is equal to 4. Dividing both sides by 2, we still end up with the same solution, y is equal to 2. In this last problem, our variable is our base. But same procedure. Let's see what this looks like as an equivalent exponential equation. So our unknown base raised to the 3rd power is equal to 27. You may know automatically what that is by looking at it. What to the 3rd power would give you 27 and have a solution. But if not, how do you undo something raised to the 3rd power? We can take the cube root of that, and we can either do it with using the radical, cube root of a to the 3rd, and what we do to one side we need to do to the other. Cube root of something to the 3rd power is that something. Cube root of 27, since 27 breaks down into 3 times 3 times 3, we have 3 3's, leaves us with 3. If you didn't use a radical, we could have, as an alternative solving this problem, we could have raised this to the 1/3 power, which is equivalent to the cube root. 3 times 1/3 would give us a to the 1st power, and raising 27 would to the 1/3 to maintain equality. Whether you translated that into cube root of 27 or understand that that denominator is the index, essentially the same, is going to give us the cube root of 27, which is 3, since 3 times 3 times 3 is 27. So our solution for our missing base would be 3 for this problem.